Okay, so we'll start going over some of the things that we discussed last time. So the main object of interest, right, is understanding the evolution of our stochastic process through this semigroup, right? So given a function f, we will define the PT operator applied to f as the conditional expectation of fxt conditioned on, I forgot, I need to condition on
the x if this is a magnitude.
x0, right? So in the initial condition. Yes, because this is going to be a function of x, right? So for a function f, we define PTF of x like this. And we discussed this enjoys the properties of semigroup, particularly that PT PS is equal to PS PT. That and that P0 is the identity, right? We also define the infinitesimal generator, which applied to a function f is defined as the limit as t goes to 0 of PTF minus f divided by t. Right, so this is the analog of the derivative. And we.
The operator is acting on the two, you said?
Well, I mean, Chewy kind of briefly discusses that. He says that the right space to work here is L2 of the invariant distribution. So we will prove that the invariant distribution.
Okay.
So in principle, you don't even know that there is an invariant distribution. So you can start working on L2 of some reference measure. But it turns out that when you take the L2 of the invariant distribution, this is going to be a symmetric operator. So self-adjoint, and self-adjointness is something that David is going to discuss. But it basically has to do with reversibility of the process. Yes. But yeah, anyways, so I think that when you start looking things in terms of the L2 of the invariant distribution, there's more structure to be understood. That's. But I should say that. So I don't know the technicalities about this whole story, but this is a great book for that. This is the Bagri Gentil Ledoux book, which I haven't read yet. But if we want to dive further into this, technicalities of these things, I think that's the right reference. Okay, we computed this infinitesimal generator for the Langevin dynamics, and we realized that it has to do with the Laplacian minus this bilinear operator involving the gradients of the function f and the potential v, right? And finally, we covered this Kolmogorov's forward and backward equations that, here's another way to see Kolmogorov's equations. So there is the, so if ut is equal to pt of f, and pi t is pt star of pi 0. So remember, pt acts on certain test functions, whereas the adjoint is going to act on probability distributions related to the initial conditions of your process, right? So the initial distribution. Then you would have that the time derivative of ut is going to be equal to L of ut. So if you notice that this is nothing but a PD, right? But what we will see, I think that when David is going to cover this more properly, this PD is going to be reflecting the density of your distribution xt, right? And that's what people call the Fokker-Planck equations. So one of these two is yeah, the evolution of the density. This is backward. This one's still forward. And this is also called the Fokker-Planck equation. Okay, so what I'm going to discuss now, and with this I will finish, is if your pi t is a stationary with respect to the evolution of the system, right? This time derivative should be 0 here. So that's going to give you a condition on how to characterize stationary distribution using the adjoint of the infinitesimal generator. Okay, so we're just going to state that result and then apply it to the Langevin diffusion. Okay, so proposition. Okay, first of all, we say pi is stationary for a Markov process if right, so if we start with some initial condition in terms of a distribution that remains, like the marginal distribution at any point in time is going to be exactly the same. And proposition. The following conditions are equivalent. First, okay, so we have these three conditions, and this should be evident from what we have just discussed, right? So the stationarity is characterized by looking at the forward equation and just letting this time derivative to be 0 because the process is stationary. That reflects on the fact that the adjoint applied to the distribution P is equal to 0. And by duality, you can also evaluate this on test functions, just using the not the adjoint, but the operator itself, the infinitesimal generator. Okay. So, yeah, I mean, I guess this is evident at this point, right? So there's no need to prove it. Okay. So, as a last, what we're going to do now is we're going to apply this theorem to the Langevin diffusion to see how to characterize the stationary distribution. So, we look at Langevin diffusion. And now we consider two functions, f, g from Rd to R, and this is just to get what I want to write now is a formula for the adjoint, right? We computed the operator L. So to compute the adjoint, if we think we're in L2, what we should do is just take two functions, and I say LFG, right? And try to get an expression that somehow leads to an integral of f times something, and that something will be the adjoint, right? Okay, we computed this L of f, right? It was the Laplacian of f minus nabla v nabla f multiplied by g. right? Using integration by parts, you can turn, I mean, you can also say, what do you want to say? Yeah, I guess using integration by parts here, you can, you're gonna get minus nabla f nabla g, right? And this other guy over here is gonna give minus nabla f nabla v times g. So yeah, at least we have now the two terms related to the gradient of f, and we can also pull that back to finally just get an expression that is going to be f times something. So for that, we can use, again, integration by parts. We're going to get f times the Laplacian of g, right? That's what you get from this term. And this guy over here, I mean, I can just also write it in this way, right? And times g, inner product. So if I use integration by parts, we're going to get f times the divergence of nabla v times g. And of course I can factorize by f here, right? So we're gonna get this, and that means that this thing over here is the adjoint of the infinitesimal generator of g. Right? Now, as we said, characterizing the stationary distribution means that this operator vanishes on that density. Right? So we need to solve this PD, basically. Okay, so conclusion, L star of G is equal to, Laplacian of G plus the divergence of G times nabla V. So pi is stationary for lifespan. If this thing vanishes, so 0 is equal to L star, let me call the density pi, right? So we have that, and then we just need to solve this equation. Now, we have to be, I mean, they propose like a clever way to solve this thing, which is noticing that if you take the divergence of pi times the, okay, so if you compute this thing, what do you get? You get by just using the product rule, you're gonna get is this right? Yeah, okay, that's the trick. So what's the gradient of the logarithm of pi? We use the chain rule, right? So you get the divergence of pi times 1 over pi times the gradient of pi. So you get that. So that means that you can replace this Laplacian of pi by this expression, and then now you can remove the divergence term. So now we get 0 equals the divergence of pi times nabla log pi plus gradient of v. So if you have that, that means that this thing must be a constant. Constant or zero? I mean, okay, let me say, one way to solve this equation is to impose that this thing is equal to 0, for instance, or equal to a constant. Yes, yes. So what you want is that gradient of logarithm of pi is equal to, I guess, minus gradient of v plus any constant. Okay, and what does this mean? I mean, it means that pi, gradient of pi? Sorry, I'm being stupid. No, we say that this is 0, this thing over here is 0. And when you integrate, you're gonna conclude that log pi is equal to minus v plus constant. And that tells you that, I mean, what is the constant? Well, this thing must be a probability density. So the constant is just gonna be the integral
of the Markov semigroup we are working with, basically. Then our PT is a symmetric operator. And if it's a symmetric operator, it basically tells us that in the products we have this equality. Then this, now here actually in the book at least they start working, they say with L2 pi, and this is where I'm not completely sure why, but they say that this symmetric operator is actually self-adjoint, so they must be working in some particular space for which that happens. But well, it's easy to see that yes, if we have this symmetric condition, then the same thing will happen for the generator. We just have to differentiate. If LF and LG are well defined, then we have this thing on the left, which could be saying that L is a symmetric operator. And actually, let's see. I'm going to write this here. This equality is also going to be satisfied, where this I'm going to define in a minute. But that's another notion that is going to turn out to be equivalent to reversibility, and also, of course, satisfied by the Langevin equation. So let's say this thing called, forgive my friends, carré du champ, which is like the square of the field. It takes its name because precisely for the Langevin diffusion, this is going to be for FF the norm of the gradient of F squared. But well, this object, when you integrate it with respect to pi, is going to be equal to this if and only if the process is reversible, and we'll see in a minute why this is true. Just, well, yeah, let's see. So, yeah, the carré du champ is defined as that. Quite important property is that it is symmetric. So if we have this equality of, without having reversibility of this object over here being equal to this, then you will have that this is also equal to this, so these two are equal and you have reversibility. Okay, and then we define the Dirichlet energy as the integral of this carré du champ. And as all good energies, we'll see that at least for FF this is greater than or equal to 0. So first let's see some properties of the objects we've already seen. The first thing that we have is that this PT is contractive on L2 of pi, and this is just by Jensen, right? So the definition Cristobal just projects down, right, of this, at least integrated with respect to this, is this condition on x0, So if you have this square by Jensen, then we have that this is bounded by these other objects. Then, just by definition again, this is precisely PT applied to F squared. And then stationarity tells us that this is equal to this, right? Because the distribution of xt would be the same as the distribution of x0, which is pi naught. The same, basically the same thing that Cristobal just used by saying that the derivative of the thing will be to be 0. Here we say that this is the identity when we integrate with respect to pi. So this is contractive in L to pi. And then, yeah, we see that not only the integral of this thing will be greater than or equal to 0, but the integrand is also greater than or equal to 0, proving that. Okay, so this, well, I should write the definition here. So this is 1/2 this applied to ft minus f lg minus g l. Okay, so for g equals f, we have 1/2 of this minus 2 times 1/2 of flf. Okay, so how do we show this? Basically, we saw that L is the time derivative of this pt. So in a slightly informal way, we can take a Taylor expansion on the pt and say that pt of f squared is f squared plus t times L applied to f squared and then little log of t. And then by Jensen, what we just did here, we have this inequality. And then we Taylor expand here as well, and we get f plus TLF plus little log of t. And then we take the square, and we get f squared. We get the square of this guy would be just little log of t, and then we get 2 times this times this. Okay. So now we just cancel the f's, divide by t, and make t tend to 0, and then we get exactly that property, right? Okay.
So I mean, property 1 is already a proof, right?
Yeah.
That this thing is non-expansive.
Yeah.
I guess they're doing it just to give some intuition. Or, okay.
Yes.
Mhm.
Okay, and now if we have reversibility, then we have this thing here that I call 1, I will call 1 for some time. So, well, this is just the same property we just mentioned. L applied to any function with respect to pi is going to be 0 by stationarity of pi. And then if we just write down the integral of the carré Duchamp, then the first thing that we get is, let's see, I didn't write the minus, right? So this should be like this, or I had in the first slide a minus here. So first thing we have is minus L applied to this thing, which by this property is going to be 0. And then we have these two things. And if we have reversibility, then they are exactly equal. That's precisely the condition of reversibility. These two are the same. So that would be equal to that thing over here. Okay. And as I mentioned before, because it's symmetric, then that implies reversibility as well. It's an equivalent condition. Okay, so another property. If we have reversibility, then PT is a positive operator and L is a negative one. Okay, I have this later, but actually the book gives a very nice intuition. It says that because we have the time derivative of PT is L PT, then we can formally write PT as the exponential of TL. Because we have reversibility, these things are symmetric, so you should expect that they have real spectra. And also, because this can be expressed as this, then you would expect that PT is a positive operator. And contractivity would tell you that this is a negative operator. That's like at an intuitive level, right? But we can just show it now. So reversibility tells you, well, first the Markov Semigroups property tells you that PT is the same thing as PT halves times PT halves, right? And reversibility tells you that you can move this here, and then that's pt of f squared, which is non-negative, and therefore it integrates to something greater than or equal to 0. So indeed, pt is a positive operator, this is greater than or equal to 0. And now we can do the same thing for L, so minus L should be positive. And so this is precisely this by this property, right? So remember, this is also under reversibility, which is equivalent to this. This is equal to the Dirichlet energy, which we showed before, that is greater than or equal to 0. Okay. So, well, this is just basically the same thing I said. It's quite useful as well to do, I will do this later, to do something like this, but maybe at higher order, that you can expand at higher orders and you will have these L's appearing. Okay, so, and now here's again where they use the symmetric of L as the adjoint. So again, I don't know exactly in which space we are working, but that property must hold in order for this to make sense. Right, so if they say that before, and all the things they were doing, they were just considering L2 of like the Lebesgue measure or something, and then the adjoint was not equal to the adjoint of L was not equal to L, but here, if we have this reversibility property, then if we consider the relative density, then the Fokker-Planck equation that was written as this, as just Christopher did before, then becomes this. Okay, so this would be really the saying that the adjoint is the symmetric. We have this, the symmetricity, but we are saying that it's equal to the adjoint. And now we are going to assume reversibility for the rest. Okay, so we want to see conditions that tells us that we can converge to the stationary distribution fast. So for that, it would be nice to see if we have like this guy, if we have like a lower bound on the spectra of minus f, then we would be converging exponentially to this distribution, right? That turns out that it is not possible because we know that L applied to constant functions is 0. So it's going to be basically true up to that. If we project something on the orthogonal space to constant functions, then we could expect that we have some non-zero minimum eigenvalue of the minus L operator, and then we could have that thing. Right? So this is the definition. It's not going to be a proof. It's something that you have to prove for your process. That it's basically saying encapsulating that thing. So Markov process is said to satisfy the Poincaré inequality if we have a certain constant, such that for all functions, this thing, which is actually the Dirichlet energy, is greater than or equal than 1 over that constant. So this 1 over the Poincaré constant will be the minimum eigenvalue of minus L of this minus the projection on the orthogonal space to the constants, which is actually equal to the variance of f, because this would be just the projection onto the constant functions, and that is telling us that we like that vector is the one that minimizes the expectation square of the expectation of the norm square f minus any constant, and that gives you exactly the mean. So that is equal to the variance. Okay. Yeah, so this is basically the same thing I said. Like here for constant function, this is 0, but this is greater than or equal to that outside of that space. Okay. And now we have this convergence quite easily. Actually, we have this thing. So we have the following equivalences. This is satisfied. The Markov process satisfies the Poincaré inequality. And for all f in L2 pi, they just normalize to have mean 0 with a loss of generality to simplify a little bit things. And then for all t greater than 0, we have this exponential convergence, right? So this thing that was contractive is actually going to decay exponentially with respect to f, which could be p0 applied to f at the rate that depends on this constant. And yeah, this is also equal to the variance and equal to the variance of this condition.
So the last equality, what?
This one
Is-
is we are just assuming.
Ah, okay, okay. No, just it's not without the exponential factor, right?
Oh, I missed the constant.
That
part,
same
yeah.
factor should be there.
Yeah, that factor should be there. Sure. Okay. So, and then you have basically the dual property, which tells you, I will write down exactly what's the definition of this chi-square, but this is basically the variance of pt applied to pi 0, which is pi t. Because pt is also a symmetric operator, it will be also self-adjoint. So the Fokker-Planck equation that we had before tells us that precisely this applied to something that depends on pi t. Actually, not pi t exactly, because the definition of this thing is going to be the same. But let's see it. Okay. So first, 1 implies 2. So we have Poincaré inequality. We want to show this exponential decay for the functions. We're just going to use the zero meaning assumption, and then we differentiate this guy. So this guy is this guy by this assumption, and we are going to take a time derivative from that. So this is equal to the time derivative of this guy and the expectation squared. However, note that by stationarity, pt applied to any function is going to be the same integral. So this thing is the integral of f d pi, and does not depend on time. So when we differentiate, that's going to cancel, goes away. So we just are left with this term. And now we want to differentiate that term, and basically for that, we can use this thing. Right, so we put the differential inside, and then we get that the differential is 2pt f and the derivative of ptf. Well, actually, you don't even need to use this because we already saw before that the time derivative of pt was lpt. So it's like this lpt applied to f. And this is by 1 equal to the Dirichlet energy at this and this, right? So it's basically saying instead of f here, we are taking ptf and ptf, because the Dirichlet energy was the integral of the Carré reduction. Okay. So, and now just by the assumption of the Poincaré inequality, let me just show you again what it was. Right, it was just that the Dirichlet energy is lower bounded by some constant, and then the variance. So here we use the same, and then again the variance as in here is just this guy. And now we have a differential equation on the variance depending on time. So this is going to decay exponentially, and the constant is going to be like the initial condition, which, as I said before, is p0 applied to f. Okay, so now in order to obtain that inequality, we basically integrate it with respect to these guys. Now to do the opposite, we just need to differentiate, because all of these were equalities. The only thing that was left was this. If we want to prove the Poincaré inequality, it's pretty natural that if we differentiate, we obtain it from the previous condition. Right, so we start with the Dirichlet energy. We want to show it's lower bounded by 1 over constant of Poincaré inequality times the variance, but I put a 2 here just to simplify. I think basically to do the same thing we have here. So that is, by definition, the variance of f minus the variance of this other guy, right? Because it is equal to this, right? Integral of f and the derivative of minus L applied to f. Right, but now we have an inequality for this from property 2. So this stays the same. This is going to be bounded by this guy and the variance as well. And now we just need to take the limit and see that precisely what we get is this 2 divided by 0.5. constant. Okay, so now to show that holds also for distributions, first let me define the divergence we're working with. We're defining the chi-square divergence between two distributions as this relative density minus 1. And note that this is just the expectation of this guy because we are integrating with respect to pi, right? So here we will have like d mu d pi, and integrates to 1 because mu is a probability distribution. So this is actually as well equal to the variance of this d mu d pi. Of course, this is only going to make sense if we have absolute continuity, and otherwise we define this as infinity. Okay, so now, and here's where I'm not completely sure why you can, well, this is fine actually. You can just always like take f equal to this guy, and more or less things, seems like everything is fine, but the theorem actually says that 3 implies 2. So it is somehow saying that the functions you can take are the same as the probability distributions up to some rescaling. So it seems we're working in that kind of space. That's where it makes sense to work with these things and take the symmetric of this being equal to its adjoint. Okay, so by just using the Fokker-Planck equation, which is what I said before, right? We apply now P to this relative density that gives us the relative density of pi at time t, and then this is just a reformulation of what we had before. This guy over here being this would be yes, right. This could be the variance of pi 0 with respect to pi minus 1. It would be nice to have like 2 screens so I can 2 slides at the same time. Right, it's just this same thing. This variance that was in the inequality is put in here pi 0 with respect to pi, or pi t with respect to pi, and then we get the exact same thing. The only technicality is that thing that in order to have the converse, then you should be able to say that these guys are all the functions you can work with up to some rescue.
They need to be in L2, right? That's
yeah.
Which is not obvious, or isn't it? Is it? Not necessarily, right?
Yeah.
Because your assumption of pi 0 is that maybe pi 0 is in L2, but why the ratio minus 1 would be, right?
Yes. Yeah.
Okay.
I'm not really not sure about how that steps down.
No, I mean for the sake of this group, we're just assuming everything that we need. But yeah.
Yeah.
Okay.
So here we're just assuming that this operator was only defined to be symmetric, is going to be self-adjoint, and that this thing is actually happening as well to let us go to 2 from 3 by also substituting. Okay. So now we are going to see actually that the Langevin diffusion is going down the gradient flow of this energy. This is just a property that these processes have as well in general. So what does that mean to begin with, right? So the gradient should be dysfunctional that lives in L2 pi, such that if we take any curve with initial conditions f, then we have that when we integrate that in that direction, it gives us the time derivative at time 0 of this curve is precisely, we want it to be, sorry, what was it doing? Yeah, this should be equal to this in order to be a gradient. But now what is this? So this, for this, we are going to use this property, so the integral of this is equal to the Dirichlet energy. So at ut, we put ut here, so just by definition, it is this guy. And now we want to differentiate that guy, and in order to do that, we just take a derivative of this at 0 is going to be this, and then we just put this at ut equals 0, and then that gives us this, and then the other derivative is going to hold basically by reversibility, right? We don't differentiate with respect to this, and that gives us s, and then we differentiate with respect to this, and gives us ut0, but this is equal to the same integral where minus L has been put here. Or in other words, like L was already time derivative, so it should commute with respect to this other time derivative as well. So we get 2 times this entry. Okay, so now we're saying that.
So I have several questions here. So E of f is E of f comma f.
Yes, it is.
Okay, that's one, and the other is where is the time dependence? You're taking the derivative at 0. Okay,
Yeah.
That's fine. Thanks.
Okay, yeah, so we found something that when integrated with respect to any direction, right, this is equal to this. So this guy is the times 2 is the function of you're looking for. This is the gradient of the Dirichlet energy. So what does that mean? That basically means that, let's see how did this work.
I mean,
Right. So the definition of gradient flow with respect to this gradient is just saying that the derivative of a curve is going always in the minus direction of the gradient. And we just saw that this gradient is equal to this guy. Right. So this curve is actually, up to the rescaling time and removing these 2, is using the same definition as the Markov process that we had. Like in every infinitesimal time step, it is advancing through the generator. So that shows precisely that the Markov process is doing that gradient flow.
is that also? I mean, does that also correspond to this Kolmogorov's forward or backward? I forgot. But the one involving
I think
L,
it's
right?
the backward equation.
Backward equation.
Yeah.
Okay.
Yeah, that was also defining the process, I think.
Right.
Yeah, I think it's an equivalence as well. You can go recover the process from that
Yep.
equation. Okay. So now I'm just going to see how those things play with the Langevin diffusion. So that's Cristobal did with this. I'm just going to pick up the same computations, but now I'm going to compute the Gauss-Duchamp, etc., and see how these properties work for Langevin. Okay, so basically, by definition, what do we have? We want to write down this guy. And this was, so I think you have it here written, right?
The L, but I didn't
Yeah, I
write
just
the
need the L, right? I need F minus L. FLG is going to be F, and this should be LG. Right? Did you have it?
Yeah, that's
here?
what you have in the first line, right?
Right, exactly. Okay, yeah, because we have reversibility, that is the same
yes.
thing.
Mhm.
And then we have the symmetric form, right? So that these two give us this and this. And now, okay, how was it that this was the Laplacian of this thing?
I mean, you're applying the definition of L to the product, at least in the first line, right? There's.
Oh yeah, but why was okay? I missed this thing. Exactly.
Yeah, yeah,
Yes.
exactly, so-
Yeah. Okay, no, so this is just the definition. Yeah, I was not looking at this. Okay, so now we just have to expand everything basically to see how this works out. So this gives these two things, and now and this as well, and now this is just going to be this by the gradient, and then this thing is, well, I changed the order, but this is this, and this is that. Okay, so now everything should cancel. So we have this 1/2 with this 2 goes away, and this is going to be the last thing. And now this is going to go with this with that, and then this gradient of V times G gradient of F is here with this minus plus, and this minus is going to cancel. The same thing happens here, minus plus, and we get this and that. So we have this. Okay, it's just a bit cumbersome computations. Actually, I wanted to do it this way so you see this thing, but the most important part, which is the one that shows why the name of this guy is carré de champ is that when you evaluate this type as well. Gamma at ff is the carré de champ, the square of the field. Okay. Okay, this type as well. All right, and now the important thing is that just with this, we can show this identity that we show that is equal to reversibility. So by just testing this, we can see that the Lagrange diffusion is reversible. So that is just a simple integration by parts. So this is the integral of the carré du champ, and then this should be just the other guy, like G minus LF by that definition that we have over here. So it's basically this guy. So we want this to be 0, and this is basically true by integration by parts. We can, for instance, look at this and differentiate with respect to all the terms, and we get those 3 terms, right? So we are using that the density of pi is proportional to the exponential minus v. When we differentiate with respect to that density, it's going to give us a minus gradient of v. Okay, so this being 0 means this is true, and then the Lagrange diffusion is reversible with respect to pi. Okay, and then this last thing is just saying, okay, how were we writing? So I'm not proving anything here, and just saying how were we writing the Poincaré inequality. We're just saying that the variance with respect to pi divided by the constant of Poincaré is lower bound in the Dirichlet energy. Now the Dirichlet energy, because gamma ff is this guy, then is this expectation, and I just moved the constant here. So if we prove for some function this thing, then we will have
So
inequality.
you need this to be true for every f, or for?
Yeah. Yeah.
So it's a property of pi, or rather the infinitesimal generator. Right?
Yeah. Yeah. So it has to call for all functions.
So the question then it's, I mean, in the case of Langevin, for instance, it would be a property of the potential V that induces this Poincaré inequality, for
Yeah.
instance.
Exactly. Yeah. At the end of the day, I guess the most useful thing is showing that we converge the stationary distribution fast. I don't know if people are interested at all in looking at 1F and therefore not showing it completely for the stationary distribution.
I think later in the book they said, for instance, if V is strongly convex, then you do have, I don't know if Poincaré inequality or log Sobolev or something that implies exponential convergence to the stationary distribution.
Yeah.
Yeah.
Okay, so that's actually all I prepared for today. Then, yeah, the next thing would be like log Sobolev, which is a similar condition that given an inequality that like this gives us convergence in KL divergence instead of chi-square divergence.
Yeah, and I think those are the maybe closer to what you want to have for sampling, right?
Yeah.
Okay, yeah. Thanks a lot.
So I'm supposed to